Hello friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers. All the candidates who are joining me live, just quickly confirm your presence in the comment section and tell me whether my audio, visual quality, everything is clear so that we can start with the session. Till you are going to report me this, let me just brief you what is the ideal duration and what is the agenda for today's session. The ideal duration for today's session is going to be approximately 45 minutes. And the agenda for today's session is that today we are going to discuss some of the important concepts and questions for your topic, the construction of synchronous generators. Everybody who is joining me live, just quickly confirm your presence in the comment section. And just quickly hit the like button, like, share and subscribe. Just quickly hit the like button, like, share it with your friends and colleagues and subscribe to BYJU'S Exam Prep if you have not subscribed till now, so that you do not miss any of the important session from your favorite faculty. So let us start with the session. Before that, some of you may be joining me for the first time, so there is a brief introduction about myself. My name is Ashutosh. As you can see on the screen, I have 11 plus years of teaching experience, completed MTech from BYJU in 2010. I have written a couple of books on ethics in power system, and my areas of expertise are this. Let us start with the first question. The first question talks about, for a 3-phase 16 poles alternator having 144 slots, what is the distribution factor? What is the distribution factor? Before we talk about this, let me just give you a brief idea about synchronous machine, especially synchronous generator, related to its construction, so that you are able to follow what we are going to discuss in today's session. If you talk about synchronous generator, like any other machine, it is going to have basically two parts. One is stator and the other one is rotor. If you see, the stator of your synchronous machine or synchronous generator is going to be similar to the stator which you have in case of a 3-phase induction motor. It means your stator is going to have a distributed winding, and which is 120 degree displaced in space, much like the stator winding of an induction motor. Let us talk about the rotor. In case of rotor, basically we have two types of constructions. The first one is cylindrical rotor, and the other one is salient type or salient pole rotor. Generally, the cylindrical rotor is going to have less number of poles. It means number of poles are generally 2 or 4. So when number of poles are going to be less, like 2 or 4, if you see the synchronous speed at which this cylindrical rotor is going to be operating, that is going to be ns 120 f upon p. Now because the number of poles are less comparatively, therefore the synchronous speed at which the cylindrical rotor machine is going to be operating, that is going to be very high. So generally cylindrical rotor is going to be suitable in those applications where we have steam turbine. Are you getting that? Suppose you have thermal power plant, coal-based thermal power plant, you are dealing with the steam turbine. This is also called as turbo alternator. Because of this reason, this is also called as turbo alternator, dealing with the steam turbine. When you are dealing with the salient pole rotor, you can identify just by their construction itself, because their poles are protruding. They are not cylindrical. You must understand, for a cylindrical rotor, the air gap between the rotor and the stator periphery is going to be constant everywhere. The air gap is constant. But when you talk about the salient pole rotor, the rotor actually looks something like this. This is what we call as a salient pole rotor. So it has a minimum air gap along the direct axis and maximum air gap along the quadrature axis, and that is why when we write the equivalent circuit of a salient pole machine or we model it in terms of the electrical network, we use two reactances. That is nothing but the two reaction theory by Blondel, that is direct axis synchronous reactance and quadrature axis synchronous reactance. Generally, this salient pole rotor is going to have high number of poles. Number of poles are going to be really high. It can be 8, 10, 12 and even more. So if you observe, in case of salient pole rotor, the synchronous speed is going to be somewhere here 120 F upon P, because number of poles are very high, so synchronous speed is less. Generally, this type of construction we are using for the hydroelectric plants. So this is also called as hydro alternator. Hydro alternator. Is it clear, everybody? Are you able to follow this? Everybody just hit the like button. Tell me in the comment section, are you able to follow this or not? Now, if you talk about rotor, generally the field winding is given on the rotor. Generally, the field winding is given on the rotor. When we talk about synchronous generator especially, I will tell you why. And if you see the stator, we are keeping the armature winding. What is the reason? The reason is field winding is going to carry the current for the field excitation, current for developing the main field flux in the machine. And the field excitation in case of synchronous generator is going to be DC excitation. But when you talk about the armature winding of a synchronous generator is going to carry huge amount of current, because we are generating power at a very high level. For example, in terms of megawatts. So the current value is going to be very high. When the current value is very high, in order to carry that current, the size of the armature winding is going to be bulky. Now, this much bulky armature winding, it is very difficult to have the rotational nature, and it is very difficult to provide effective cooling also. So, especially in case of synchronous generator, what we are doing, we are keeping this armature winding at the stator so that it is stationary, and we are making the field, that is the field winding, that is DC excitation, to be on the rotor side. Is it clear for everybody? Just tell me in the comment section. Are you able to follow this? The other construction is also possible. It means you can keep the field winding on the stator and you can keep the armature winding on the rotor. But generally for a small size it is okay, but for a large size machine, for example synchronous generator, you are generating power up to megawatts. So in order to reduce the rotational losses and to provide the effective cooling, we are keeping the armature winding on the stator, that is the stationary part, and we are keeping the field winding on the rotor side. Is it clear for everybody? Are you able to follow this? Now, as I have already explained, the stator is going to have the distributed winding. Now, the distributed windings are going to be something like this. I am just giving you some brief idea. Please try to understand. There are going to be slots in the inner periphery of the stator, something like this. Suppose this is the center. So, we are defining the angle subtended by one slot. This is what we are calling as beta. What is this beta? Beta we are defining as the slot angle. Beta we are defining as the slot angle. Is it clear, everybody? Yes? Now, if you see the question, it is very simple. If you directly apply the distribution factor formula KD, it is going to be sine m beta by 2 divided by m sine beta by 2. What is m here? M is number of slots per pole. So what is going to be the value of M? Number of slots are 144. Number of slots per pole per phase. So number of phases are 3 and number of poles are 16. Just solve this value. How much you are getting the M value? Then how to calculate this beta? Beta we are defining as 180 degree electrical divided by number of slots per pole. Number of slots per pole. How many number of slots you are having? 180 degree electrical divided by number of slots are 144 and number of poles are 16. So you can solve these two values. Just put it here and you will be getting the distribution factor. As per my reference, I think you must be getting it somewhere around 0.96. 0.96. Everybody just tell me in the comment section, are you able to follow this? Yes, everyone. How we are defining beta? Beta is actually the slot angle. Now, how we are writing this equation for beta, if you want to understand, you can understand. See what is happening here. If I ask you what is the total angle? What is the total angle? For one pole pitch, what is the angle? For one pole pitch, it means from one north pole to one south pole. What is the pole pitch? It is 180 degree electrical. So if there are P number of poles, what is going to be the total angle? It is going to be how much? It is going to be 180 degree electrical, that is the pole pitch, multiplied by number of poles divided by number of slots. You will be getting the slot angle. Yes or no? What is beta? Beta is slot angle, the angle subtended by one slot. So if you know the total angle divided by the number of slots, you will get the slot angle. How we are finding the total angle? The angle subtended by one pole pitch, one north pole to one south pole, is 180 degree electrical. So if there are P number of poles, so the total angle will be 180 degree multiplied by P divided by S. Is it clear? Now you keep this P here and it will become 180 degree divided by number of slots per pole. Is it clear? See the next question. What is the distribution factor for a uniformly distributed winding, three-phase winding having a phase spread of 60 degree? Now let us try to understand what is the meaning of uniformly distributed winding. As we have already seen, if you see the inner periphery of the stator, something like this. Something like this. Now what is happening? If this is your cylindrical rotor, suppose this is your cylindrical rotor. If you observe the air gap, because of these slots, there is going to be a non-uniformity in terms of the air gap. In case of the slot, the air gap is high. In case of a teeth, this is what we call as teeth or tooth, and this is what we call as slot. So when there is a slot, the air gap is high. When there is a teeth, the air gap is minimum. Because of this reason, the output that you are getting from this generator is not going to be sinusoidal, it is going to be something like this. So these type of harmonics are going to be present in the output of your synchronous generator. We want to avoid these slot harmonics. How to avoid these slot harmonics? If anyhow we can increase the number of slots. If you increase the number of slots, then this disturbance is going to be less. Why? Because if you increase the number of slots, the slot angle is going to be very less. Are you getting this or not? So slot angle is going to be very less, very small. Now when slot angle is very small, I am writing this distribution factor for the uniformly distributed winding as sine m beta by 2 divided by m sine beta by 2. Now for the uniformly distributed winding, beta is a very small value, so we can say sine beta by 2 is approximately equal to beta by 2. So just write it here. It will become sine m beta by 2 divided by m beta by 2. What is this m beta? This m beta we are defining as sigma, that is the phase spread. That is the phase spread. How we are defining phase spread? What is m? Number of slots per pole per phase. It means within one phase, under one phase, and under one pole, how many slots are there? If you multiply it with the slot angle, it will give you the phase spread. Are you getting this or not, everybody? Tell me in the comment section, are you able to follow this or not? Yes, Shubhadeep. Now this phase spread is mentioned, so directly you can apply this formula for the distributed winding, uniformly distributed winding, as sine sigma by 2 divided by sigma by 2. But there is an important concept here. When you are writing the angle like this, you have to convert it into the radians. You cannot write it in the degrees. For example, this is going to be sine. What is the phase spread? It is 60 degree. Divided by, this is going to be 60 degree. Now we have to change it to the radians. So divide by 180 degree multiplied by pi. Just try to solve this and you will be getting your answer. Yes, everyone? As for my reference, you must be getting 0.955. C is the correct option for this. Everybody just tell me, are you able to follow this? Are you able to follow this? Tell me yes or no. See the next question. This question talks about the excitation EMF, how to calculate the excitation EMF if the power transferred is given. He is saying there is a synchronous generator with a synchronous reactance of 1.2 per unit. So the situation is something like this. This is your synchronous generator and this is the reactance of that synchronous generator. Is connected to an infinite bus whose voltage is 1 per unit through an equivalent reactance. Now in between there is one equivalent reactance and now it is connected to a infinite bus. The infinite bus is having the voltage as 1 per unit. The excitation EMF is here. Reactance is 1.2. This reactance is 0.3. He is saying what should be the value of EMF, that is the excitation EMF, to give a maximum output of 1.2 per unit. What is the meaning of maximum output? The real power transferred by this synchronous generator to the infinite bus is going to be something like this. This you can write as P is equal to mod Eg mod V upon X equivalent, and this is going to be sine del. If you want P to be P max, then del has to be 90 degree. Then you will be getting sine del as 1. What is this P max? This P max is given in the problem and that is 1.2. So this is 1.2. Excitation EMF Eg per unit voltage is 1. What is the total equivalent reactance? Just add the synchronous reactance and the equivalent reactance corrected through the bus, infinite bus and the generator. 1.2 plus 0.3 is 1.5. So this is 1.5. So if you solve this, I think you must be getting the magnitude of the excitation EMF as 1.8 per unit. Is it clear, everybody? Are you able to solve this or not? So what is the answer you are getting? D. See the next question. A three-phase induction motor draws 100 kVA at a power factor of 0.8 lagging. A synchronous condenser is connected in parallel to draw an additional 750 kVA at 0.6 power factor lead. He is asking what is the power factor of the total load supplied by the mains. It is basically a power factor improvement question, okay, not directly related to the construction part, but we can solve it. That is related to synchronous generator only. or synchronous machine only. So he is saying there is an induction motor. Okay, suppose there is an induction motor. It is connected to the system, and here you are connecting a synchronous condenser. Okay, so let us connect a synchronous condenser. Suppose this is your synchronous condenser. He is saying the induction motor is drawing 1000 kVA at 0.8 power factor. 1000 kVA at 0.8 power factor lagging. About this synchronous condenser, he is saying a synchronous condenser is connected in parallel to draw an additional 750 kVA at 0.6 power factor lead. Now this synchronous condenser he is saying it is taking 750 kVA at 0.6 power factor lead. The same information I can represent as this much power he is giving to the system, that is 0.6 power factor lag. Are you getting that or not? Is it clear? Actually, this synchronous condenser is supplying lagging reactive power to the system. So either you can say it is supplying lagging power, reactive power to the system, or you can say it is taking leading reactive power from the system. That is the same thing. Now what he is asking in the question is, what is the power factor of the total load supplied by the mains? So power factor we are going to observe by observing what is the situation for the reactive power. Now if you observe the reactive power, what is going to be the reactive power drawn by this induction motor? This is 1000 and this is 0.6. Why? Because you have to write the kVA, that is S, and you have to write sin phi, that is S sin phi. So this is going to be 600 kVAR. If you see the reactive power supplied, lagging reactive power supplied by this synchronous condenser to the system, it is going to be 750 multiplied by, this is going to be 0.8, because sin phi here is going to be 0.8, 0.6 is cos phi. This is also going to be 600 kVAR. Now this is very interesting. It means the reactive power supplied by the synchronous condenser is exactly matching the reactive power absorbed by the induction motor. It means the burden of reactive power on the supply is 0. Is it clear? When the burden of reactive power on the supply is 0, then what is going to be the operating power factor of the system? That is going to be unity. Is it clear, everybody? Are you able to follow this? So this is all from my side for today's session. Let us stop here and let us meet tomorrow. We are going to discuss the parallel operation of generators. Okay, there is one more question. Let us do this question also. One more question is there. 3-phase 4-pole 48 slots. The coil span is 1 to 9th slot. He is asking then what is the pitch factor. How we define the pitch factor? If alpha is the chording angle, then how we are defining the pitch factor? It is cos alpha by 2. So we are interested in this alpha. Let us try to understand what is this alpha. He is saying there are 9 slots. So let me first make 9 slots. Okay. Suppose this is the first slot, second slot, third slot, fourth, fifth, sixth, seventh, 8th, 9th. When he is saying there are 9 slots for the coil span Coil span means one coil side is in the first slot and the other coil side is in the 9th slot. So the situation is something like this. One coil side is here and the other coil side is here. So what is going to be coil span? Can you tell me what is going to be coil span? How we define coil span? See here. How we are defining coil span? Suppose this is north pole, this is south pole, and your winding is something like this. This is what we are defining as the coil span. This is the coil span. This is also called as coil pitch. Now this coil span, if suppose we are calling it as gamma, if this gamma is equal to the pole pitch, what is pole pitch? Pole pitch is 180 degree electrical, then this is called a full pitched coil. Then this is a full pitched coil. But generally, because of various advantages we can discuss later, we are having short pitch coil. In the short pitch coil, what we are doing, we are saving some of the conductor material, and instead of having a full pitch coil, we are having a cording angle something like this. Now this angle we are calling as cording angle alpha. So if this is going to be your coil span, this is the cording angle alpha. So can I write for a short pitch coil, it is going to be alpha plus gamma is going to be 180 degree electrical, yes or no? Now what is gamma here? How many number of slots are there? See 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8 and 8 to 9. This is 1, 2, 3, 4, 5, 6, 7, 8. It means the coil span is going to be spreading across 8 slots. So gamma is going to be 8 multiplied by beta. What is beta? Beta is the slot angle, that is 180 degree electrical divided by number of slots per pole. Is it clear for everybody? How you are going to calculate beta? It is given in the question. Beta is going to be 180 degree, number of slots 48, number of poles 4, just solve it. I think it must be coming as 15 degrees. 15 degrees. Just put it here. So this is going to be how much? 8 multiplied by 15. So this is going to be 120 degrees. Yes or no? So if gamma is coming as 120 degree, what is going to be alpha? Alpha is going to be 180 degree minus gamma. So 180 degree minus 120 degree, this is going to be 60. So what is going to be pitch factor? It is cos 60 degree divided by 2. That is cos 30. What is cos 30? Root 3 divided by 2. So what is going to be your answer? D. So D is going to be your correct answer. So this is all from my side, friends. Thank you so much for joining me live in the discussion. I hope you enjoyed the session. Do not forget to like, share and subscribe. Do subscribe the channel so that you do not miss any of the important session by your favorite faculty. And let us meet tomorrow when we will discuss the parallel operation of alternators. Thank you so much. Take care of yourself. Thank you. Thank you, everyone. Thank you. Thank you, everybody. Take care.